We're now going to consider our final category of particles, messenger particles. So messenger particles carry the fundamental forces. Formally, these messenger particles are known as gauge bosons. So let's start with the electromagnetic force. For the electromagnetic force, the carrier particle is the photon. So let's have a think about how we can actually apply this to what we've already learnt about. So previously you've learnt about Coulomb's law, which tells you about the force between a positive particle and a negative particle. Well, how do they know that the other particle is actually there? Within this theory, we have what's known as virtual photons. So our positive particle sends out virtual photons towards our negative particle. The negative particle detects these virtual photons and they're messenger particles. They're actually telling the negative particle that the positive particle is here, and so then the negative particle feels the force from the positive particle. Now these are known as virtual photons because we cannot actually do experiments to detect them. Now, one thing that you might be puzzling over is, well, can we just create particles out of nothing, or does that violate a whole lot of laws of physics? Well, we've seen the Heisenberg uncertainty principle before, which tells us that we do have delta E, delta T has got to be greater than or equal to h bar on 2, but this does allow us to create a certain amount of energy, a very small amount of energy for a very small amount of time without violating any rules. So these messenger particles are only created for a very, very, very short period of time, and this does not violate any of the rules that we've learnt about so far. Now for the weak nuclear force, we've actually got 3 carrier particles. We've got the plus and minus W boson and the Z boson. Now the photon was a massless particle. For the weak nuclear force, the W and Z bosons do have mass. These W and Z bosons were discovered in 1983 in a particle accelerator at CERN. So let's have a think about an example of how we can apply these W and Z bosons to something that we've already seen. We've seen how beta decay previously, how a neutron can decay into a proton plus an electron and an anti-electron neutrino. So let's have a think about what's going on in terms of these carrier particles here. So essentially the neutron, we've learnt about quarks, it consists of a down, down and up quark, and the proton consists of an up, up and down quark. So essentially how we're getting from the neutron to the proton is we're transforming a down quark into an up quark. So we can actually rewrite this equation as a down quark goes to an up quark, and then in this process we actually create a W minus boson. The W minus boson then immediately decays into an electron and an anti-electron neutrino. Now the strong nuclear force is carried by a particle called the gluon. The strong nuclear force is actually sometimes called the color force because gluons are able to change the color of the quark. As we talked about when we were discussing quarks, they always need to combine in colorless combinations. So how could we transfer a red quark into being a green quark? If we wanted to transform the color of that quark, the red quark is going to have to absorb an anti-red bit of color and then also a green bit of color in order to first of all cancel out its red color and then make it green. So gluons actually carry a color and an anti-color, and this allows all the quarks to transfer between the different types of colors. So just as a point of interest, you've possibly heard of quantum chromodynamics before, QCD. This has got the chromo in the word, meaning color, because of this strong nuclear force being known as the colored force. Now, gravity is a problem for us at the moment. There's not really a nice explanation for how gravity works. So some theories do require a gauge boson for gravity known as the graviton, but this has not yet been observed. We discovered the Higgs boson, it's been predicted for quite a while, but it was discovered from accelerator experiments just a few years ago. So the Higgs boson's not a gauge boson, it's a scalar boson. And the Higgs boson is needed to give particles mass. So this has been detected, but it's not the same thing as a graviton. So many physicists would like to create a grand unified theory where we can describe all four of the fundamental forces within the one theory. So a lot of work is being done in that space at the moment.